Section 4.2, proving triangles congruent by the side-side-side postulate and the side-angle-side postulate. On the side-side-side postulate, or the abbreviated version SSS postulate, if three sides of one triangle are congruent to three sides of another triangle, then the two triangles are congruent. In our previous section, we know that we needed to prove triangles congruent by getting three sides of one triangle congruent to three sides of another triangle, and the three angles of one triangle congruent to three angles of another triangle. In other words, we needed to prove 6 things to get the triangles congruent. Here we have a shortcut version. Our first shortcut version is the side-side-side postulate. In the diagram, I do have the side-side-side postulate diagrammed. Here I have triangle ABC and XYZ that have 3 corresponding sides congruent. We can identify them by the single, double, and triple ticks. Now, all I need to do is set up a congruent statement. In this triangle, I'm going to go from single, double, to triple. Therefore, ABC is congruent to triangle, and single, double, to triple is going to be XYZ. And I'm allowed to state that because of the side-side-side postulate, a great shortcut to be able to use to prove triangles congruent. Next, we need to identify what an included side and an angle is. Here we have an included side, a side between 2 angles in a triangle. To identify that, I have a diagram, triangle ABC, and I've identified included sides. For example, segment AB is between angle A and B. Here's angle A and B, and segment AB is sandwiched in between the 2 angles. And that's kind of the way to look at it. If the segment is sandwiched in between the 2 angles, it is included between those 2 angles. Segment BC is sandwiched between angle B and C, and segment AC is sandwiched between angle A and C. In other words, they're included sides when they're sandwiched between the 2 angles. An included angle is an angle between 2 sides in a triangle. In other words, it is the segments that form the angle that we're going to identify as being included. Here I have triangle PQR. And let's identify some included angles. Here I have angle P. It is included and between the sides of the triangle PQ and PR. PQ and PR are the segments that form angle P. Angle Q is between QP and QR. Those are sides of the triangle, but also are the segments of the angle. And finally, angle R is included between the sides of the triangle RP and RQ. And RP and RQ are also the segments that form that angle. Another way to look at it is the same way we identified the previous included sides. It's sandwiched in between the sides of the triangle or the segments that form that angle. We needed that definition to use our next shortcut to prove triangles congruent. Our next shortcut is called side-angle-side postulate, or abbreviated SAS. If 2 sides and an included angle of one triangle are congruent to 2 sides and an included angle of another triangle, then the triangles are congruent. In the diagram, I have illustrated the side-angle-side postulate. I'm given triangle ABC and triangle XYZ. We could notice that I have segment AB congruent to segment XY and CB congruent to segment YZ. That's true because of the single ticks and the double ticks. And angle B is included between my 2 congruent sides on triangle ABC, and angle Y is included between the 2 congruent sides on triangle XYZ. Therefore, they are corresponding and match up, and I can use the side-angle-side postulate to state the triangle, and I'm going to go single to the arc to double, which is ABC. Single arc double is XYZ, my congruent statement. And I can state this is true by the side-angle-side postulate. Again, a great shortcut. Instead of using 6 correspondences to get triangles congruent, I now need 3 to prove triangles congruent, as long as they're in the correct format, which those 2 formats we know now are side-side-side and side angle side. Our first example is a proof, and here they want me to prove triangle FGE congruent to triangle HGE. In previous sections, we needed to prove 3 segments of this triangle congruent to 3 segments of this triangle, 3 angles of this triangle congruent to 3 angles of this triangle. Let's see if we can use our shortcuts to get these 2 triangles congruent. Our given information is that EG bisects segment FH. When that's true, G is the midpoint of FH, and I can state that segment FG is congruent to segment GH. And that is by the definition of midpoint, or also definition of segment bisector. Now I can put tick marks in to illustrate that. I'm given that segment EF is congruent to segment EH. Now I'm very close to both of my shortcuts. If I'm going to use side angle side, I would need to prove my included angles, which are angle F and angle H congruent. But I have no information to do that. But I do have a property of congruence that I can use, which is stating that segment EG is congruent to segment EG by the reflexive property. And when I look at the diagram, I see I have side, side, side. Now I can state, and I'm going to use the congruent statement given, which is triangle FGE is congruent to triangle HGE. And that is by the side, side, side postulate. Again, we want to prove triangles congruent. Here I have triangle LMN congruent to triangle NLO. Again, let's see if we can use some of our shortcuts. Here I'm given that segment LM is parallel to NO. And I'll illustrate that in my diagram. And I'm also given that segment LM is congruent to NO. Now, I know that these 2 segments are parallel. I'm going to label these 2 angles 1 and 2. And I can see if 2 parallel lines are cut by a transversal, then alternate interior angles are congruent. So angle 1 is congruent to angle 2 by the AIA theorem. I can state that these 2 are alternate interior angles, but I can't state they're congruent because these 2 lines are not parallel. But I can still use one of my shortcuts if I can get LN congruent to LN. And I can by the reflexive property. And now in my diagram, I can see I have side, angle, side, side, angle, side. Therefore, I can state triangle, and I'm going to use their congruent statement, L, M, N, congruent to triangle, N, O, L, by the side, angle, side postulate. On this slide, they just want me to answer the questions based on the diagram triangle X, Y, Z. Number 1, what sides include angle Y? Those are the sides that form that angle. So I start at the vertice, Y, and my sides of that angle are YX and YZ. Number 2, what angles include segment XZ? Actually, those are the endpoints of the segment which would make up angle X and angle Z. Number 3, what angle is included between segment XY and XZ? I don't need to look at the diagram, but I will. But first, the easiest way is to look at the segments. X is in both segments. Therefore, XZ and XY. The included angle is angle X. And last, what side is included between angle X and angle Y? Angle X and Y are the endpoints of this segment that is included, which would be segment X, Y. On this slide, can you determine if the triangles are congruent? If so, write a congruent statement and name the postulate used. If not, write not possible. In this diagram, I have segments in each triangle that are congruent. Here, AC is congruent to CE, BC is congruent to CD. I can state that these two angles are congruent by the vertical angle theorem. Then I can state the triangles are congruent by side, angle, side. A congruent statement would be, and I'm going to go from single tick to arc to double tick, which would be ACB, triangle ACB, is congruent to. Again, I'm going to go from single tick to single arc to double, which would be ECD. On this triangle, I already can identify side, side, side because I have a single, a double, triple, and a single, double, triple. Therefore, these two triangles are congruent by side, side, side. And I'm going to go in that order, single, double, triple, which would be HIL, is congruent to triangle, single, double, triple, IJK. On this diagram, I see I have two sides congruent because they have the same measure. I can't identify if the third sides are congruent. Therefore, this is not possible. If I knew that these two segments are congruent, then I could use side, 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 but I don't. On these two triangles, I know I have these two segments that are parallel. Therefore, I can state that this angle and this angle are congruent because of the AIA theorem. If two parallel lines are cut by a transversal, then alternate interior angles are congruent. Similarly, I can do that with these two angles for the same reason, AIA theorem. Then I can state that these two are congruent by either two methods. The two-angle theorem, if two angles of one triangle are congruent to two angles of another triangle, the third angles are congruent, or by the vertical angle theorem. In other case, I have all the angles congruent in each triangle, but I don't have any sides being congruent. Therefore, this is not possible. These two triangles are not congruent by the long method or by any of our shortcuts. From the given information, can you determine if the triangles are congruent? I'm given triangle ABC and triangle DEF with angle B congruent to angle E, segment BA congruent to ED, and segment AC congruent to DF. Let's just draw each triangle. A, B, C, D, E, F. I know angle B is congruent to angle E. I know segment BA is congruent to segment ED. And I know segment AC is congruent to segment DF. This looks like it's side angle side, but this angle is not included between my congruent sides. Therefore, this is not side angle side. For this to be side angle side, I would need angle A congruent to angle D. Therefore, this is not possible.